Hello everyone, we are going to start section 4.9, the last section in chapter 4. We're going to talk about rank, nullity, and fundamental matrix spaces. In the previous section, we learned that using the matrix, we can build three major matrix spaces. First, we can cut the matrix into rows, and these rows are going to create, or like linear combinations of these rows are going to create row space. Also, we can cut matrix into columns, and columns as vectors are going to create a column vector space. Also, general solution of homogeneous equation Ax equals 0 is going to consist out of some vectors, and these vectors are going to linear combinations, are going to create another space which is called null space, right? So we are going to start today with definition. Definition is going to talk about numbers. We remember from like previous sections that if you take matrix A and do row operations on that matrix, we can reduce it to like reduced echelon form, and this reduced echelon form is going to have some like 0 rows and some leading ones, and basically we can find out a basis for row space this way, right? The rows which are not going to disappear while you are doing the row space are going to row operations are going to create a basis for row space. I'm going to have an example over here. Somebody took matrix A and did modified it, used row operations on it, and did reduced echelon form. So let's look at, eventually, like once in a while, we had matrix A, and then we did row operations, and we got reduced echelon form. You see my reduced echelon form I created is very simple, just to make a good example for like illustrating my definition. So let's first look at the definition. Definition tells that rank of matrix A is equal dimension of row space or column space. We are going to show that row space and column space have some dimension. Remember, dimension is amount of vectors in the basis, right? So row space is going to have a basis, and number of vectors in that row space basis is going to be called dimension of that row space, and we are going to also call this dimension a special word, rank of matrix A. So basically, dimension of row space is going to be called rank of matrix A. Nullity of matrix A is going to be dimension of null space. Well, null space is a space of solutions of homogeneous equation Ax equals 0, right? And null space is going to have also some basis, some vectors. We can count how many vectors we have in that basis, and we are going to call it dimension of null space. And also for matrices, we are going to call it nullity. Okay, so two major numbers for matrices, rank and nullity. Rank is number of independent rows, and nullity is dimension of null space or solution space, right? Let's consider somebody gives us a reduced echelon form, and this forms this like the system has like 5 variables, 3 equations, and when you are doing row operations, or somebody was doing row operations, we totally eliminated row number 3. So what we have over here, if we count how many rows we have left, we actually have left 2 rows, and these 2 rows are going to create a basis, right? And which means that dimension of row space is going to be equal to. Now, how many leading ones do we have? Leading ones, we have 1 and we have 2. Well, we remember from the previous section that row operations do change column space. Column space is changing, but row operations don't change the fact that some columns are linearly dependent or linearly independent. We see obviously that column number 1 and column number 2 are linearly independent. There is no way you can kind of multiply column number 1 by something and get column number 2. Same column number 2, multiply by something and get column number 1. So basis of column space, and we have dimension of column space. Space here is also 2. Well, you see why actually over here we say that the column space or row space are going to kind of have same dimension, because we put in the definition it's dimension of row space or column space. We are assuming that it's the same dimension. Again, why? Because dimension of a row space, it's amount of like non-zero rows in a matrix, and this is like what we see, right? Dimension of column space is amount of leading ones, amount of columns with leading ones, and we do also have the same amount, like, because they are actually essentially same. The rows with leading ones are the same as columns with leading one, right? Same amount. So that's why we are going to kind of name this dimension by special name rank. Nullity. Well, nullity is, generally speaking, dimension of solution space. And how do we find dimension of solution space? Well, you probably see that here, guys, we do have two leading ones. We have two leading ones. And how many free variables we have? Well, we have 1, 2, 3 free variables, which are going to produce 3 parameters. And eventually, you are going to get like 3 vectors in the solution, and they are going to be linearly independent, and they are going to create a basis of null space. So basically, guys, dimension of null space here is going to be 3. And if you look carefully, you're going to see that these 2 number of like dimension of row space and these 3 dimension of null space are making up 5 number of variables. Well, why is this? Well, just because if something is not having leading ones, if variable does not have leading one, it's going to be a free variable. So means that like the variable is going to produce a parameter, and how many parameters we're going to have? That's 3. And the rest is going to be like, so we have 2 plus 3 is going to be equal 5. I'm going to write it down as an equation in terms of like dimension. So what is 2? Rank, right? 2 is rank of matrix A. What is 3? 3 is nullity. Of matrix A. And 5 is number of variables. So that's going to be a major equation for like, let's say, accounting for matrices. What I want to do, guys, I want to kind of solve this reduced row echelon form and show you how solution is going to look and why we are actually going to have 3 linearly independent vectors in it. It's going to be very, very simple solution. So we see that we do have 3 free variables. I'm going to set up x5 equals p, x4 equals t, and x3 equals, well, let's name it s, right? So now I'm going to write down equation number 2, do back substitution, and that's going to be what? x2 plus 0, x3 plus 0, x4 plus 0, x5 equals 0, homogeneous equation, right? From where we can see that 0, 0, 0, and that's going to mean that x2 equals 0. Well, 0 solution of one variable is not bad. So we have 0. And the last equation, the first one actually, we call it last, but that's going to be the first equation, is going to look like this. x1 plus 2x2 plus 3x3 plus 4x4 plus 5x5 equals 0, right? Now I'm going to put solutions which I already know. Let me make it a little bit smaller. So I don't know x1, so I'm going to keep it. 2x2, sorry, let me put it on one side first. Plus 2 multiplied by 0. I know that x2 is equal to 0 plus 3x3. 3s plus 4t and plus 5p equals 0, from where I can calculate that x1 equals what? Minus 3s minus 4t minus 5p. Well, I picked up the reduced row echelon form to make solution very, very quick. Now I'm going to write down like the vector solution. Remember, how do we write down vector solution? Vector solution is going to be x1, x2, x3, x4, x4, and x5. I'm going to write them down first as like solutions and then convert them into vectors. So x1 is minus 3s minus 4t minus 5p. x2 is 0. x3 is what? S. x4 is t. And x5 is p, right? Now I'm going to write it down as a vector. x1, x2, x3, x4, and the x5. So what we have? Well, I'm going to first put parameter s. And I'm going to look like by what s is multiplied in every vector. I see minus 3 for x1. I see like 0 here. And then I see 1 for x3, and then 0 and 0 for x4 and x5. There is no s here, right? No s here, no s here, no s here. So my first parameter plus. Well, let's do like t next. Next parameter is t, and I'm going to have minus 4 for x1, 0, 0, 1, 0. And last one is p, and that's going to be minus 5, 0, 0, 0, 1, right? Now, guys, let's look at how our solution looks. First, how many vectors we have? Obviously, we have 3 vectors, right? Second, do you see that these vectors are linearly independent? How can we see this? Well, if you watch what happens to 1, over here, 1 sits in the last position. Over here, well, next to last, and over here, like next to last, right? You won't be able to express any of these vectors through others just because of this one, because you see that we do have 1 and zeros in other positions. So no matter by what you multiply this vector and this one, you won't be able to get this one just because there are zeros over here. And that's going to like happen when you solve it. So these 3 vectors are linearly independent, and dimension is going to be equal to 3. So I'm going to write down nullity of A equals 3. Okay? Wow, that was just like a simple example. Okay, now what else do we need to know about those magic spaces? Well, there are lots of theorems about like how everything is combined, like if you have number of equations less than number of variables, more than number of variables. I do not want to discuss those theorems. I want you to look up in the book, because if I discuss every theorem in this section, it's going to take like an hour of the video. What I want to discuss major or most interesting theorems. My next theorem I'm going to discuss is going to be that if A is any matrix, then rank of A equals rank of A transpose. Well, this is a very, very simple theorem. I'm going to prove it just in one line. So what is rank of A? Rank of A is dimension of row space, right? Dimension of row space is equal dimension of column space, right? And columns are making rows for transpose matrix, means that it's going to make rank. Well, let me do one more step here. One more step. Dimension of a row of AT transpose matrix, because columns of A matrix are making rows and transpose matrix, and that's going to be equal rank of AT. Well, kind of obvious, but still needs to be stated that it's going to work like that. Right? What else? Well, because of this, guys, remember we had a nice equation over here that rank of A plus nullity of A equal number of variables. For transpose matrix, we can write down like the same equation. So rank of A transpose plus nullity of A transpose, and number of variables is not going to be equal to n, because like, you know, n is number of columns. Number of variables is going to be equal to m, which is number of rows. So if this is matrix A, this is n, and this is number of rows, right? For matrix AT, we are going to have it opposite. We're going to have m over here and n over here. So number of variables for transpose matrix is going to be m. Now, we know that this one is going to be equal to rank of A from the theorem, right? For nullity, we don't know what it's going to be, but you see that nullity, we can tell that, for example, if rank of A is equal to R plus nullity of A transpose, or like space of solution space of like transpose matrix equals m, we know that nullity is going to be m minus rank. If you look over here, nullity of original matrix, let me go back to the equation. Nullity of original matrix is n minus rank. So nullity of A transpose is m minus rank. This is just like some accounting for, like, you know, for matrix spaces. Okay. Basically, that's all. And again, to find rank and nullity of a matrix, we will need to convert it into reduced echelon form. I'm going to consider example, just like a typical example of like finding example. Find typical problem. Find rank and nullity of A, which is equal to 2, 0, minus 1, 4, 0, minus 2, 0, 0, 0. Well, again, I'm trying to consider very, very simple examples so you can kind of see like how to solve it. So, well, guys, you probably see that row number 1 and row number 2 are identical, just multiplied by 2. Well, what I'm going to do, I'm going to actually do this row operation. Row number 2 equals row number 2 minus 2 row number 1. And because they're actually multiples of each other, I'm going to get the matrix looking like this. 2, 0, minus 1, 0, 0, 0, 0, 0, 0. You see? Well, again, just I designed matrix to be solved in one step. So what we see, guys, if you divide row number 1 by 2, you are going to have number of leading ones, which is going to be 1, right? So we are going to write down that rank of matrix A equals 1, right? What is going to be nullity? Number of free variables. Well, free variables are going to be x2 and x3, right? So nullity of A is 2. And the sum of rank and nullity is going to be equal number of variables 3. So 1 plus 2 will be equal 3, number of variables. Well, basically just like typical problem. Okay, well, sometimes, usually the question about nullity and rank is not going to come by itself. Usually it's going to come as some conclusion of the problem. For example, somebody is going to ask you to solve a linear system of equations and then ask additional questions like what is nullity, what is rank. Usually questions don't come by themselves in like real problems, exam problems or homework problems. Okay, that's all about this section, and I suggest you to go over this section in the book because there are some other theorems which I don't stop because just like video is going to be too long. It's already like 20 minutes long, and like additional like 3-4 theorems are going to make it longer. We are going to talk about those theorems in class. So here I just considered like 2 major theorems. Okay, and see you in class.